Think about the physical effort it takes to lift something heavy. When you hoist a solid block straight up off the floor, you are performing mechanical work against the downward pull of Earth's gravity. This chart tracks energy in real time. We calculate surface work by multiplying mass, the acceleration of gravity, and height. W equals mgh. But this math assumes the variable g stays locked at 9.8 meters per second squared, regardless of height. If we zoom out past the atmosphere into the cosmos, that assumption fails. At planetary scales, the distance between objects stretches into thousands of miles. As you move further from Earth, the actual force of its gravitational pull decays. In deep space, gravity is no longer a constant number. Because this force weakens continuously over distance, our standard surface-level equations are inadequate. To calculate energy across the solar system, we need a universal framework that accounts for this decay. This universal framework is built on the concept of a conservative force. In physics, a force is conservative if the total work required to move an object between 2 points depends only on those positions, not on the path taken to get there. Watch these two masses travel from Earth to the same point in space. One flies in a direct line, the other takes an erratic, zigzag detour. Despite the different trajectories, the final energy expended is identical for both. Stripping away the detour reveals that the only variables required for the calculation are the initial distance, r1, and the final distance, r2, from the center of the planet. Defining gravity as a conservative force allows us to build a predictable mathematical model for planetary energy that remains valid regardless of an object's specific flight path. This chart visualizes the calculation. Because the force of gravity weakens every inch you travel, we cannot use simple multiplication. We must use calculus to add up infinitesimally small slices of work across the entire distance. This integration results in the universal equation for gravitational potential energy. The energy at distance r equals negative big G, the universal gravitational constant, times the mass of the Earth and the object, divided by r plus a constant, W1. This relationship describes every gravitational interaction in the universe, governing any system of multiple masses, regardless of their size or location. Take a system of 4 masses at the corners of a square. To find the total potential energy, we sum the energy of every individual pair. That means calculating the 4 outer edges and the 2 inner diagonals, totaling 6 distinct connections. The total energy of the universe is the mathematical sum of millions of these individual conservative pathways interacting at once. This brings us back to the constant, W1. If we want to use this equation, we have to decide where the universe places its baseline zero value for gravitational energy. In orbital mechanics, physicists define the absolute zero point of gravitational potential energy at an infinite distance, far beyond the reach of any planetary body. The logic follows the physics of decay. As you move further out, the gravitational pull between 2 objects weakens. At a theoretical infinite distance, that pull finally reaches zero. Shifting our zero point to infinity changes how we must evaluate an object's energy as it moves closer to a planet. If we start with zero energy at infinity, what happens to that value as a mass falls toward the Earth? This grid maps the descent. Because Earth's gravity pulls the object in, the system loses potential energy, dropping below zero into this dipping funnel. This is why gravitational potential energy is inherently negative everywhere except at infinity. Removing the test mass leaves Earth's permanent influence on the surrounding space. This empty well is gravitational potential, the potential energy per unit mass. It is the permanent shape of space, waiting for an object to enter it. Ultimately, that energy is negative because the gravity well is a hole in the fabric of space. To return to the absolute zero of infinity, you must perform positive work to climb back out.